So common multiples. For each of the following choices of C and D, find CD, 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 and CD. Basically, again, not quite like that though. It's basically when you say this, the GCD of C and D is with normal parentheses. It can also be stated as CD. It's just parentheses, and brackets can be used for LCM quite often. So you're finding GCD, LCM, least common multiple, greatest common divisor, least common multiple, the product of the GCD and LCM, and of course C times D. For 3 problems, we have different values of A and D. Means yeah, no, C and D. So if C equals 8 and D equals 12, you basically factor like before for greatest common divisor. 2 cubed and 2 squared become like the same, so it's actually 2 squared that gets the common divisor. Because it's 2 times 2 times 2, yeah, so 2 cubed is 8, and 12 is 3 times 2 times, it's 3 times 2 squared. Becomes 2 squared is the lowest form of it, what they share in common, is the lowest power. So that's why it's 2 to the squared, which to the second power, which equals 4. The least common multiple, you take the largest, you take if it's something is shared, you take the largest exponent of it, and you also multiply everything that's not shared together with what's shared. So here you just multiply 2 cubed times 3, even though it's 2 cubed, 3, and 2 squared. You do the largest, so that's why I circled those. So 2 cubed times 3 equals 8 times 3, which equals 24. And that's your LCM, or the CD with brackets around it. Square brackets. And of course, GCD times LCM will equal 4 times 24, which equals 96. And C times D equals 8 times 12, which equals 96, just like the GCD times LCM. Because a little known fact is that the product of GCD and LCM will equal what the GCD and LCM of for the same two numbers. Product of the two numbers. So this is just trying to show off that property really is what's going on here. And I stated in simple terms, CD equals 4, 24 is the brackets. And then, but I don't think it's that complicated. And more examples of this. C equals 7 and D equals 35. Greatest common divisor is just 7, because 1 times 7 and 5 times 7 is what they factor down to when you break them up into primes, the multiples of primes. And the least common multiple, it's 7 times 5, because that's all that they come up, because 5 times 7 and 1 times 7, basically, you could think of it that way. 7 is shared, but just to the 1 power regardless. So it's 7 times 5 equals 35. And then you do this, the greatest common divisor times the least common multiple of the same two numbers, which equals 7 times 35, which equals 245. And C times D is equal to 7 times 35, which equals 245. Yes. And that's your chart here. Then finally C equals 3 and D equals 14. The greatest common divisor is just 1. This would mean that they're relatively prime as well, 3 and 14, which makes sense via eyeball. That doesn't seem like numbers that would really have anything in common vision-wise, really, except for 1. We just shown you. And the greatest common divisor is 1. The least common multiple is 3 times 2 times 7, which equals 42. Because that's what the factor down to be, 2 times 7 and 1 times 3. So 314, so basically the GCD times the LCM equals 1 times 42, which equals 42. And of course C times D is equal to 3 times 14, which equals 42. Yeah. So that's just a use of least common multiple calculations. So find GCD of BC given that A, B, and C are integers with GCD AB equals 14 and we want to find GCD of BC, and we're given GCD of AB as a solid number. And we're also given several situations. The first one is A equals 31 plus B. 31B plus C. Which there's a theorem that states that GCD of AB is equal to GCD BC if we have this, if we have this condition A equals 31B plus C, A equals QB plus C is satisfied. So we can write it like this. Basically, this means GCD of BC is equal to 14 because that's what GCD of AB is. And the second one is just the same, but just a little bit one extra step. So it's 33B minus C is what A is equal to now. So it'd be equal to GCD of B negative C in this case. But the little known fact is that one of the properties of the greatest common divisor is that GCD of a number in negative is the same as both the positives. So GCD of BC is equal to GCD of B negative C. In the end, you basically GCD of B negative C is 14 because it's equal to GCD AB, and then the next thing is GCD of BC equals GCD of B negative C. So GCD of BC equals 14. So you can see this is just like a trick. You have to use a theorem or two for these problems. That's one theorem. That's use another one. Some implications. So congruence of C modulo B, that's equivalent to B divides A minus C, and that further implies that A minus C equals B times Q. We'll just say Q is any number, and that implies that A equals BQ plus C. Yep. Seems like we have an order. So GCD of AB, is still equal to 14, of course, and it's equal to GCD of BC. So GCD of BC is equal to 14. So. And this one, same type of thing. Pretty much, except for we have a negative, so it's just one extra step. So A congruence, this negative C modulo B is equivalent to B divides A plus C. B divides A plus C implies that A plus C equals B times Q, which implies that A equals BQ minus C. Yeah, and then we basically do GCD of AB equals GCD of B negative C. And then GCD of B negative C equals 14 because GCD of AB is always equal to 14 in this problem. So and also GCD of B negative C equals GCD of BC because we're using that's a property of the greatest common divisor. So GCD of BC equals 14. Okay, now it's time for a proof, sort of, more of a showing how it works. So let A, B, and C be integers with AC equals 1, so the greatest common divisor of A and C is 1, and the greatest common divisor of B and C is 1. Show that C and A times B, the product of AB, are relatively prime. So using one theorem's two corollaries, basically. And I have marked page 23, but regardless. We're using two parts of it, but in kind of the reverse, like we're using the second parts in the first part, pretty much. Sort of almost like a reverse, but it's not fully. But so GCD of AC equals 1 implies that 1 equals AE plus CF, where these are all integers, And same as 1 equals BG plus CH for B and C. Okay, then we just multiply the two equations together, which we can do. Don't act shocked. 1 equals 1 times 1, so that's just 1. In the book, they give you a hint, basically, to do this. They give you, like, some of the equations, like the form them equal to 1 and then show this end equation of A times B times X plus C times Y equals 1. But you have to figure this out. Point is, you basically have the product of them, which is ABEG plus BCFG plus ACEH plus C squared FH equals 1. And to simplify this left-hand side, we want to get it so that we basically, the point is you want to get a linear combination of A, B, and C. And if that's equal to 1, then you can say, you can go backwards to get a GCD equal to 1, basically. So this whole basically you factor out AB from here to get, it's just one number, but it's AB times EG. Parentheses emphasize it's AB times the number. Plus C, we factor out C out of each of these terms. C times BFG plus AEH plus CFH equals 1. And it's A times B times X plus C times Y equals 1. X and Y are integers, and X equals EG, and Y equals that thing, that list of that expression. So an ABX plus CY equals 1 is equivalent to GCD of AB and C. So A times B and C equals 1. That's what I mean by AB here. Productivity. And the correlated CM2, gives us that. And of course, GCD of AB, product AB and C equals 1 implies that C and AB are relatively prime by definition, because that's what relatively prime means. The greatest common divisor between the two numbers are 1. Is 1. Finally, let A equals 39, B equals 42, and C equals 45. Find A and greatest common divisor of A, B, and AC. This first part. Same process before. You can just look at the work here, all from one page, because it's relatively simple work. But yeah, only 3 is shared here, because it's 3 times 13. It's 3 times 2 times 7. The greatest common divisor of A and C, they have 3 as well. 3 squared times 5 and 3 times 13. Just take the lowest power. And then the second part is find the least common multiple of AB and AC. Basically, least common multiple of the GCD of AB and the GCD of AC. So this is LCM of basically 3, 3. Which, as simple as it sounds, it's literally just 3. The LCM of 3, 3 is 3. It's equals 3. Because, you just they only share 3 within themselves, so you can't really do anything. So 3, find BC. This is the least common multiple of B and C. So 42, 45, and 2 times 3 times 7, and 3 squared times 5. This means it's going to be 3 squared. That would be 2 times 3 squared times 5 times 7. 90, which is 9 times 7, which is equal to 630. 630. Okay, that's the least common multiple. Then that's part 3, and then part 4 is find the greatest common divisor of A and the least common multiple of B and C. The greatest common divisor of those two numbers. So this is GCD of A LCM BC, which is equal to GCD of 38 LCM 42 45. Or 39, I mean. Yeah. And basically, if you have that, the LCM of 42 45 equals 630, as said before, and GCD of 39 630. And of course, it would be 2 times 3 times 5 times 7, and 39 is only 3 times 13 when it's factored down. So the GCD is 3. And for the last part, are the answers the same in parts 2 and 4? So 2, we got this, we got 3, and 4, we got 3, so yes. And I suppose they're trying to show a property or an idea, which is all fine and good, but sometimes it's just basic doing this work to show stuff.